In the beginning there was nothing, or so we are told. An endless black silence, a void without form, without structure, without even the faintest breath of being. Yet even here, in the deepest absence we can imagine, something stirs. A flicker, a pulse, a phantom whisper of existence that appears, quivers, and vanishes before the eye can blink. It is gone before it was ever truly there. But was it ever there at all? This is the paradox at the heart of quantum physics. In the emptiness between stars, in the vacuum of space itself, the laws of nature permit impossibilities. Particles that should not exist, that cannot exist, materialize for the briefest instant and then dissolve back into the void from which they came. They are called virtual particles, but the name is misleading. They are not like particles in the ordinary sense. They are not atoms or photons or quarks. They are not things you can catch or measure, not in the way we normally think of reality. And yet their fingerprints are everywhere. Imagine looking into the abyss and realizing that it is not empty, that beneath the silence of space lies a restless sea, boiling invisibly with ceaseless creation and annihilation. Physicists describe this as the quantum vacuum, a state that seems calm on the surface, but churns with infinite possibility beneath. In this strange landscape, particles and antiparticles spring into being as pairs, dance in a fleeting embrace, and then annihilate each other, erasing the evidence of their brief rebellion against nothingness. They leave behind no corpse, no residue, only a shadow, a distortion, a subtle trace in the mathematics of quantum field theory. Some scientists insist they are merely symbols in an equation, placeholders for interactions we cannot otherwise describe. Others believe they are the ghosts of the universe, whispering secrets about the structure of reality itself. But here is the haunting truth. Whether they are real in the conventional sense or not, the universe behaves as though they exist. Without them, the laws of physics collapse. Without them, black holes would not evaporate. Without them, atoms could not hold together. Without them, the very fabric of the cosmos would unravel. And so we arrive at a strange contradiction. We live in a universe built upon the shoulders of things that may not exist, ghosts, illusions, fleeting mirages, and yet they govern everything. This is not simply a question for physicists. It is a question for all of us. What does it mean to exist? Does something need to endure, to be observed, to be touched in order to be real? Or can reality itself be woven from that which flickers, that which slips away before it can be grasped? Perhaps the more unsettling possibility is this, that what we call real is just the longest-lived flicker, that stars, galaxies, human beings, all of us are nothing more than temporary disturbances in a greater void, destined to vanish as swiftly as the ghostly particles that gave us form. Imagine a man standing in an endless desert of night. No stars, no horizon, only silence. And then, at the edge of vision, something shimmers, a mirage of water. He reaches for it, and it disappears. Was it ever there? Or was it only the mind playing tricks? Virtual particles ask the same question of the universe itself. Physicists do not see them directly. They infer their presence from the way they warp equations, from the way they leave faint traces in experiments, like footprints pressed into sand by an invisible traveler. The Casimir effect, the anomalous magnetic moment of the electron, the slow evaporation of black holes. Each of these phenomena is like a whisper pointing back to the ghosts in the void. And yet, no one has ever caught one. No one ever will. By definition, they vanish before they can be seen. This is why some physicists scoff at the idea of calling them real. To them, virtual particles are nothing more than mathematical devices, necessary fictions that make equations work. They are not particles in space, but ripples in probability, fleeting calculations that we mistake for things. In this view, the flicker in the void is not a flicker at all, but a flaw in how we are looking. But others argue differently. They insist that dismissing them as fiction is a mistake because the effects they leave behind are real. They may be brief, ephemeral, but so are lightning bolts, sparks, or the beating of a heart. To deny their reality, they say, is to deny the very mechanisms by which the universe operates. And here lies the tension that will haunt us throughout this journey, the clash between what is real in our minds and what is real in the abyss. If a particle exists for a fraction of a second, does it count as existing? If it vanishes before it can be measured, is it still real? What if the whole universe is the same, a flicker in the void, temporary, fragile, waiting to vanish? The strange truth is that physics offers no definitive answer, not yet. All it can do is show us the shadows left by ghosts. And so we find ourselves asking a question that feels more like philosophy than science. What is existence? What is reality? And are the foundations of the universe built not on stone, but on illusions? The flicker returns, a ghost in the void, a ripple in nothingness that may not exist at all. And yet without it, nothing we know would stand. So we begin here, at the edge of nothing, staring into the abyss, searching for the unreal foundations of the real, searching for the truth of the virtual. Because if the universe is built on ghosts, then the story of everything begins not with matter but with a lie. And the next question is the one that refuses to let go. If virtual particles cannot be seen, cannot be measured, cannot be touched, how do we know they are there at all? They call them virtual particles, but that name is misleading. A particle is something tangible, something you can weigh, measure, track as it dances across a detector. But these things are not that. They are whispers in the mathematics, placeholders in equations, phantoms that live in the shadows of quantum mechanics. And yet without them, the story of the universe would break apart. Imagine a world haunted by ghosts. You cannot see them directly, but you feel their presence in the way the air shifts, the way the floor creaks, the way a chill runs down your spine. Virtual particles are the ghosts of the quantum world. They flicker into existence in the equations of quantum field theory. They leave faint imprints in experiments, but they disappear the moment you turn to look at them. What separates them from the particles we know? A real electron is like a lighthouse beam, persistent and measurable, carrying charge and mass through space and time. A real photon is the messenger of light, striking your eye, letting you see the world around you. A virtual photon, on the other hand, does not travel freely through the void. It exists only as a ripple in a calculation, a bridge between interactions. It is the phantom handshake exchanged between two charged particles, unseen, unmeasured, but vital to the act of communication. This is how forces themselves are understood in the strange language of modern physics. Two electrons repel each other, and in the mathematics that repulsion is mediated by virtual photons, ghost messengers that leap from one to the other, carrying the news of force. In the nucleus of atoms, quarks cling together through the grip of the strong force. But how do they know to hold on? Virtual gluons, exchanged in an endless unseen frenzy, bind them tight. Without these ghosts, the heart of the atom would disintegrate and the universe would be nothing but dust. Yet these messengers are never caught, never isolated. They are born and die inside the equations, never venturing into the light of detection. To call them particles is almost a cruel joke, a name borrowed from a reality they never share. They are like actors in a play who exist only in the dialogue, never on the stage. And so the debate arises: are they real, or are they nothing more than accounting tricks, invented by physicists to make sense of the chaos beneath? Some argue they are simply internal lines in a Feynman diagram, mathematical conveniences with no claim to existence. To believe in them, they say, is to mistake the map for the territory, the shadow for the substance. But others point to the weight of their consequences. If they are fictions that move mountains. Without them, equations fall silent. predictions fail, and experiments collapse into nonsense. The universe itself behaves as if these ghosts are alive. Think of it this way: you do not see the wind. You see trees bend, waves crest, sand shifting across the desert floor. You infer the wind because you see what it touches. Virtual particles are the same. We see the bend, the shift, the subtle changes in the world, and so we infer the ghosts. But what kind of reality is that? Is a thing real if it cannot be seen directly, if it cannot be isolated or captured? Or is reality only what endures, what can be held in hand, what can be pinned to the wall of a laboratory? This is where physics bleeds into philosophy. The universe may be telling us that reality itself is not a matter of permanence but of influence. That which changes the world is real, whether it stands before us or hides forever in the dark. And yet the mystery deepens, for virtual particles seem to violate the very rules that govern reality. They are allowed to break the sacred laws of conservation, of energy, of momentum, of existence itself, but only for an instant. Borrowing energy they do not possess, defying the order of the cosmos before erasing themselves to balance the books. It is as if reality permits ghosts, so long as they vanish quickly enough. This raises an unsettling thought. If the universe makes room for phantoms, how many of the things we believe to be solid are themselves illusions of time and circumstance? How many of the so-called laws of nature are little more than allowances for ghosts? The mathematics insists upon their presence. Feynman diagrams, those intricate webs of interactions scrawled across blackboards, are haunted by virtual particles. Each line, each loop, each spark of possibility is animated by things that are not supposed to exist. The diagrams work, the predictions are precise, frighteningly so. But behind the elegance of the math lies a deeper unease. Are we describing reality, or only tricking ourselves with symbols that happen to fit? And if they are illusions, what does that make us? Because without them, matter itself could not hold. Every atom in your body is stabilized by forces carried by things that vanish before they can be observed. You are a being built of ghosts, your solidity a facade woven from flickers, the human body, the planet beneath your feet, the stars that burn in the sky, all of it propped up by phantoms. So which is stranger? That these things exist unseen, or that the universe can be built upon things that do not exist at all? The question lingers, uncomfortable, unresolved. The ghosts of the quantum world leave us with no easy answer. They demand we live in tension, between belief and denial, between physics and philosophy. But if we cannot decide whether they are real, then perhaps we can at least ask a different question. What proof do they leave behind? Where in the world can we see the scars of their fleeting existence? The answer lies in shadows, in experiments where the invisible makes itself known, not by showing its face, but by moving the world around it. And that brings us to the next step in this ghost story, the Casimir effect. The pressure of nothing, the touch of emptiness, the proof that what is not supposed to exist does. Imagine two flawless metal plates, polished to perfection, suspended in a vacuum. Nothing separates them, no air, no particles, no light, only emptiness. Place them a hair's breadth apart and wait. If the universe were truly empty, nothing should happen. They should remain suspended, silent, untouched for eternity. But they do not. Slowly, invisibly, inexorably, the plates begin to move. Not away from each other, but toward one another. They are drawn together by a force that has no name in classical physics, no cause in ordinary intuition. It is the hand of nothing itself pressing the two plates together. This is the Casimir effect, one of the strangest and most haunting proofs of the quantum world. It is the whisper of virtual particles made manifest. For in the so-called emptiness between the plates, something stirs. The vacuum is not barren, it is restless, alive, a storm of fluctuations flickering in and out of being. Here is how it works. Between the plates, only certain wavelengths of these invisible fluctuations can exist, their energies restricted by the narrow gap. Outside the plates, in the infinite void, all wavelengths are permitted. This imbalance creates pressure, as if the universe itself leans upon the plates. And so, with no visible cause, the plates slide together, pushed by the weight of the vacuum. Nothingness has weight. Emptiness has power. The absence of matter exerts a force. It is one of those moments where the universe betrays its strangeness in the most undeniable way. This is not metaphor, not speculation. It is experiment, repeatable and precise. The Casimir effect has been measured countless times down to exquisite levels of accuracy. It is a real phenomenon born of unreal players. The ghosts of the quantum world may not be caught, but they leave scars that cannot be denied. Think of it. The very void, which we once thought of as an endless absence, behaves instead as a crowded theater. Ghost particles popping into being, colliding, annihilating, all in silence. And in the small space between two metal plates, their restless dance creates a measurable push. For centuries, philosophers argued about the nature of nothing. Was a vacuum truly empty? Was it absence, or some subtle presence unseen? The Casimir effect is physics' unsettling answer. Nothing is not nothing. The vacuum itself is a fabric, stitched with fluctuations, alive with unseen possibility. The implications are terrifying in their elegance, because if the vacuum is alive, if emptiness is unstable, then the very foundation of reality trembles. Everything you see, every atom, every star, every galaxy, floats not on a still sea of nothingness, but on a stormy ocean of restless ghosts. And here lies the deeper question: what is more real, the thing we can see, or the force it exerts in secret? The Casimir effect compels us to admit that the invisible may be more decisive than the visible, that the world is shaped not by matter but by the fluctuations beneath. The image is haunting. Two plates drifting together not because of gravity, not because of magnetism, not because of any force we can name, but because nothing itself has a hand. This is a revelation that shakes the boundary between physics and philosophy. If the vacuum is not empty, if it brims with unseen activity, then perhaps there is no such thing as absence at all. Perhaps existence and non-existence are not opposites, but companions, intertwined. Some physicists insist on caution. They remind us that virtual particles are only one way of describing this effect, a convenient picture for what is, in truth, the restless vibration of quantum fields. But for those who stand before the experiment, who measure the invisible pressure of the void, it hardly matters whether the ghosts are real or symbolic. Their influence is undeniable. And yet, there is a darker implication still. If nothingness can move metal, what else can it move? What larger canvases does the vacuum paint upon? Could the same restless fluctuations that tug together two small plates also have sculpted the universe itself? Cosmologists whisper of quantum fluctuations in the earliest moments after the Big Bang, tiny irregularities in the seething vacuum that grew into galaxies and stars. If so, then the Casimir effect is not a mere laboratory curiosity. It is a window into the mechanism by which the cosmos itself was born. Two plates drawn together in silence, echoing the forces that shape the heavens. It is difficult not to feel the chill of awe in such moments. To think that everything we know may rest on the breath of ghosts, on fluctuations in what is supposed to be nothing. That the universe itself may be one vast Casimir effect, matter drawn together, structures formed by the restless instability of the void. And so the shadows deepen. Virtual particles, once dismissed as abstractions, reveal their fingerprints. They may not walk the stage of reality, but their footsteps echo loud enough to shake the world. If empty space can push, if nothing can exert a force, then the question becomes unavoidable. Is emptiness the greatest presence of all? And if nothing can shape the cosmos, what happens when nothing decides to unmake it? There are places in the universe where reality itself seems to tear, Black holes, titanic abysses where gravity grows so strong that even light cannot escape. To approach one is to approach the end of time itself, a horizon beyond which nothing returns. For centuries, physicists believed these cosmic monsters were eternal prisons, swallowing all who strayed too close, their interiors locked away forever from the outside universe. But then came Stephen Hawking, and with him, a revelation so shocking it seemed heresy: black holes can die. The idea begins, as so many quantum mysteries do, with the vacuum. Imagine space just outside the event horizon, the invisible boundary that marks the point of no return. To classical physics, this region should be empty, but quantum mechanics insists it cannot be. Here, just as in the Casimir effect, the void seethes with fluctuations. Virtual particles flicker into existence, particle and antiparticle paired like dancers, only to annihilate each other and return to nothing. But at the edge of a black hole, something strange can happen. If one particle of the pair falls across the event horizon while the other escapes, the annihilation never occurs. The particle that escapes becomes real, flying outward as radiation. The one that falls inward carries negative energy, subtracting from the black hole's mass. And so, with each flicker, the black hole loses a fragment of itself. This is Hawking radiation, a theft from the abyss, stolen by the ghosts of the quantum world. The consequences are staggering. Black holes, once thought immortal, are doomed to fade. Over trillions upon trillions of years, they will shrink, bleed away, and vanish entirely. The titans of the cosmos undone not by stars or collisions, but by the quiet gnawing of virtual particles, ghosts eating giants. It is an image both terrifying and sublime. The darkest places in the universe, glowing faintly with the fire of their own demise. Radiation born not from matter but from nothing itself. And yet the question lingers. Are these particles real? Do they truly exist, escaping from the jaws of the horizon? Or is Hawking's radiation another mirage, another trick of the equations? Physicists debate. Some argue the escaping particles are simply mathematical reinterpretations of quantum fields, that nothing literal is popping out of the vacuum. Others insist the process is as real as starlight, as real as heat itself. Either way, the universe behaves as though it is true. Black holes, the great devourers, are not eternal. They are fated to vanish. But if they vanish, what becomes of the information they consumed? Every book, every star, every atom swallowed by a black hole seems to be lost forever. And yet quantum mechanics insists that information cannot be destroyed. The clash between these two truths, Hawking's fading black holes and the permanence of quantum information, is one of the deepest puzzles in science. A paradox born of ghosts. For our story, what matters is this. Virtual particles, unreal phantoms that flicker into being and vanish, are given teeth at the edge of black holes. They steal mass, they alter destiny, they reshape the ultimate fate of the cosmos. If they are illusions, then they are illusions with power. If they are ghosts that kill. And here philosophy and physics meet again. If something unreal can destroy the most massive objects in the universe, what does that say about our definition of reality? Perhaps real is not what endures, but what changes. Perhaps existence is not permanence, but influence. Picture it. The great black spheres of the cosmos, glowing faintly with radiation, evaporating into the darkness. Entire galaxies may collapse and die, but the black holes will remain, slow to fade. And yet, even they cannot resist the whispering theft of the virtual. Given enough time, more time than human imagination can contain, nothing will remain but the flicker of ghosts. This is the ultimate irony. The most real thing we can imagine, a black hole, infinite gravity, unstoppable, eternal, undone by the least real thing of all. Shadows from the void, illusions in the math, slowly undoing the universe's strongest prison. The flicker becomes a flame, the unreal becomes destiny. And so, we are left with a haunting question. If black holes themselves can be unmade by the virtual, then what of the universe itself? Could the ghosts of the quantum world not only eat giants but devour all of creation? That is the spectre waiting in the shadows of cosmology, that the energy of nothing may be the most destructive force of all. What do you see when you look into the night sky? Stars, yes. Galaxies drifting like islands across a cosmic ocean. Darkness stretching endlessly between them. But look closer, deeper. That darkness is not empty. It hums with a secret force, a hidden weight, an energy so vast it dwarfs every star, every galaxy, every atom that has ever existed. It is the energy of nothing. This is one of the strangest revelations in modern physics. For centuries, scientists assumed that empty space was just that, a backdrop, a stage upon which the drama of the cosmos unfolded. But quantum mechanics shattered that illusion. Space is not a stage, it is an actor. And the vacuum, which we once imagined as barren, is in truth a seething ocean of fluctuations. Everywhere, at every moment, particles flicker into being and dissolve. Virtual photons, virtual quarks, virtual everything, rising and vanishing before we can see them. Their restless activity fills the void with energy, an energy that cannot be switched off, cannot be erased. Even if you strip away all matter, all light, all heat, the vacuum itself remains heavy with possibility. This vacuum energy is no trivial thing. Its fingerprints are written across the cosmos. In the late 1990s, astronomers peered at distant supernovae, ancient explosions shining across billions of light years, and made a discovery that shook physics to its core. The universe is not just expanding, it is accelerating. Galaxies are being driven apart faster and faster, as though some hidden hand were pushing them. That hidden hand is thought to be vacuum energy. Dark energy, as it is called, may simply be the restless pressure of virtual particles bubbling in the void. If so, then nothingness is not passive. It is the most powerful force in existence. It is not the stars that rule the cosmos, nor the galaxies, nor the black holes. It is the empty spaces between them. Consider the scale of this revelation. Everything you see, the earth beneath your feet, the sun in the sky, the Milky Way itself, makes up less than 5% of the universe. Dark matter accounts for another 27%, an invisible scaffolding that binds galaxies together. And the rest, more than 2/3 of all reality, is dark energy. It is the energy of nothing, stretching space itself, accelerating the cosmos into an unknown future. Pause on that thought. Nothing is the majority. Emptiness outweighs existence. The void is the universe. And yet, here lies the paradox that gnaws at physicists. When quantum field theory tries to calculate the energy of the vacuum, the numbers it spits out are obscene, a value so high it would tear the universe apart instantly. The prediction overshoots reality by 120 orders of magnitude. To call this the worst calculation in the history of physics is no exaggeration. It is the greatest mismatch between theory and observation ever recorded. Something is wrong. Either our equations are broken, or reality is stranger than we can imagine. Perhaps both. Some suggest that vacuum energy cancels itself out, that positive and negative contributions balance almost perfectly, leaving only a faint residue, the dark energy we see. Others whisper of hidden dimensions, new fields, new physics waiting just beyond reach. But whatever the truth, the message is clear. We do not yet understand the nothing that rules us. And so, the ghosts of virtual particles rise again. Are they real, or are they illusions in the math? If they are illusions, then why do they push galaxies apart? If they are real, then why do they predict infinities? The vacuum does not answer. It only expands, accelerating into mystery. There is a philosophical chill in all this, for it suggests that creation and destruction are not opposites, but twins. that the same fluctuations that seeded galaxies in the young universe now pull them apart in its old age, that the vacuum, restless and alive, is both womb and tomb. Picture the end. Trillions of years from now, stars will exhaust their fuel. Galaxies will drift apart until their light can no longer reach us. Black holes will fade into nothing, and still, the vacuum will push, stretching space until it becomes cold and thin and lonely, a universe emptied not by collapse but by expansion, a silence born not from absence but from the energy of absence itself. Nothing will win. And so we arrive at a thought that is almost unbearable, that the universe is not built on matter at all, but on its opposite. That existence is a brief, fragile decoration upon the true monarch, the void. This is the lesson of dark energy, the lesson of vacuum energy, the lesson of ghosts, that the real power lies not in the visible, but in the invisible, not in being, but in nothingness. But if the vacuum carries energy, if it shapes destiny, then a darker question waits in the shadows. What if that energy is unstable? What if the vacuum itself is not the ground state of reality, but a false one? Because if the energy of nothing can push galaxies apart, then perhaps it can also collapse them in an instant. Perhaps the void is not just restless, but dangerous. And if that is true, then everything we know, the stars, the earth, every breath, every thought, rests upon a fabric that may one day rip without warning. There is a sickness in our mathematics, a hidden crack that runs through the most successful theory in the history of science. Quantum field theory has predicted the behavior of particles with a precision so exact it defies belief. Measurements of the electron's magnetic moment agree with theory to 10 decimal places. Nothing in science has ever worked so well. And yet, when this same framework turns its gaze to the vacuum, it fails spectacularly. It predicts infinities. At first, infinities in mathematics can be dismissed as curiosities, artifacts of an incomplete model. But in quantum physics, they appear everywhere. Try to calculate the energy of the vacuum, the restless sea of virtual particles bubbling in the void, and the answer climbs without bound. Every frequency, every vibration, every possible fluctuation adds to the sum. And because there are infinitely many possibilities, the total energy is infinite. An infinite vacuum would not be silent. It would scream. Its energy would crush matter, collapse galaxies, shred the universe into nothing in an instant. Yet here we are, in a universe that is calm, stable, enduring. The contradiction is staggering. The most successful equations in history predict not just the wrong number, but a catastrophic impossibility. Physicists confronted this horror and reached for a desperate tool, renormalization. A method that takes the infinities, sweeps them into a corner, and redefines the theory in terms of quantities we can measure. It works. It gives answers that match experiment. It allows us to continue, to build technologies, to expand knowledge. But it feels like cheating. Imagine constructing a cathedral on rotten stone. From the outside, it towers, magnificent, every arch perfect. But beneath, the foundation is cracked. Renormalization is like patching the cracks with paper. It holds, for now. But the unease lingers. Richard Feynman himself, one of the fathers of quantum electrodynamics, admitted as much. He called renormalization a dippy process, absurd in its very logic, but astonishingly effective. It is a cure that works without explaining the disease. And so we live with infinities, ghosts in the math that remind us we do not truly understand the foundations of our universe. The vacuum energy problem is the most dramatic of these. Quantum field theory predicts a vacuum energy density 1 × 10 to the 120 power times larger than what we observe as dark energy. This is not a small error. It is the worst prediction in physics. If you were to calculate the distance from Earth to the Sun and miss by 10 to the power of 120 times, your answer would overshoot the size of the observable universe by a number so vast it defies imagination. This mismatch is called the cosmological constant problem. Einstein once introduced the constant to hold the universe in place, then discarded it when the expansion of the cosmos was discovered. Now it has returned, but in a darker form. We know there is vacuum energy. We know it drives cosmic acceleration. But we cannot explain why it is so small, why the ghosts of the void do not drown us in their infinite tide. The problem runs deeper still. Every field contributes. The electromagnetic field, the Higgs field, the gluon field, all of them bubbling with fluctuations. Add them together and the numbers explode. And yet, the universe balances delicately on a knife's edge, expanding slowly, not tearing apart. Why? No one knows. This is where physics begins to resemble theology. Some invoke fine-tuning, the idea that the constants of nature are adjusted with uncanny precision to permit a stable universe. Others suggest the multiverse, an infinite collection of realities, each with different vacuum energies, most hostile to life. We exist, they say, in the one universe where the numbers happen to allow us. But these are not answers, only evasions. The infinities remain, mocking us. And so we confront a possibility more unsettling still, that our mathematics, brilliant though it is, has reached its limit. That quantum field theory is not the final story, but only a chapter. That the true nature of reality lies deeper, beneath the ghosts, beneath the infinities, in a place we cannot yet reach. What does it mean for science when its most precise theory collapses under the weight of its own equations? It means humility. It means admitting that the foundations of physics rest not on bedrock, but on shifting sand. It means living in the tension between success and failure, precision and paradox. For the ordinary person, this might feel abstract. But think of it this way: every device you own, every laser, every computer chip, every GPS satellite, all depend on quantum field theory working flawlessly. And it does. But at the same time, it predicts a universe that should not exist. We are like sailors navigating a sea by a map that is both uncannily accurate and fundamentally wrong. The map brings us to port, time and again, yet it insists the ocean should not exist at all. And this is where the ghosts of the virtual world deepen their mystery. If they are unreal, why do they break our equations? If they are real, why do they predict infinities? Perhaps they are neither real nor unreal, but something stranger, a reflection of a deeper order we cannot yet name. There is, of course, a darker implication. If the vacuum truly holds infinite energy, then perhaps our calm universe is an illusion, a fragile bubble in a storm too vast to see. Perhaps one day the balance will break. The infinities we patch away with mathematics will come rushing in, and reality will unravel. The thought is terrifying, but it is also a reminder that the line between existence and non-existence is thin, fragile, trembling with uncertainty. That the universe itself is not a fortress, but a precarious edifice perched on the edge of infinity. And so, the infinities problem is not just a failure of physics, it is a whisper from the void. A warning that what we call reality may be an approximation, a temporary pattern in a chaos we cannot comprehend. The ghosts press closer, the equations scream, and we are left with the question that physics cannot answer. Is reality stable? Or are we perched on the brink of collapse, sustained only by the mercy of illusions? If infinities lurk beneath everything, then perhaps reality itself is a borrowed state, temporary, fragile, destined to vanish. And so we end this chapter at the edge of dread. For the next question is more unsettling still. If virtual particles live on borrowed time, what does it mean to borrow from the universe itself? At the heart of the quantum world lies a bargain, a deal struck between existence and non-existence, enforced not by law but by uncertainty. It is here that virtual particles draw their breath, not from permanence, not from substance, but from permission granted by the most unsettling principle in physics, the uncertainty principle. Heisenberg's insight was as devastating as it was simple. The more precisely you know one property of a particle, say its position, the less precisely you can know another, such as its momentum. This is not a matter of faulty instruments. It is not a weakness in our technology. It is a fundamental truth about the universe. The quantum world is built not on certainty, but on limits. And hidden within this principle is a loophole, a cosmic indulgence that allows impossibilities to exist. If you cannot know both energy and time with perfect precision, then energy itself can fluctuate briefly without consequence. The universe looks away for an instant, and in that blink, particles may be born from nothing. They borrow energy they do not possess, live for a fleeting heartbeat, and vanish before the books can be balanced. It is a loan from reality, and the debt must be paid in full. Virtual particles are the borrowers. They appear not because they are allowed, but because the uncertainty principle forbids us from declaring they cannot. For the briefest slivers of time, the universe tolerates their theft. The smaller the loan, the longer they may persist. The larger the theft, the swifter their annihilation. Always, the scales must balance. This is why we cannot see them. By the time we try to measure, they are gone. Their very existence is tied to evasion, to slipping away before the gaze can settle. They are born in secrecy and die in silence, their presence inferred only from the tremors they leave behind. It is a haunting image, a cosmos, where the very fabric of reality runs on credit, where the void itself is a marketplace of theft and repayment, of fluctuations forever settling their debts. And yet, what they achieve in their brief existence is profound. Consider the forces that hold atoms together, that bind matter, that shape stars and galaxies. Each is mediated by the unseen hand of virtual particles, ghostly messengers darting between matter, carrying whispers of force, borrowing reality just long enough to deliver their news. Without them, nothing would cohere. Matter would disintegrate. The universe would dissolve. So we arrive at a paradox. The building blocks of the cosmos depend on things that cannot be said to exist. Reality rests upon borrowed time, borrowed energy, borrowed being. And what does this mean for us? If the foundation of the world is built on loans from nothing, then perhaps existence itself is debt. We are all fluctuations, temporary disturbances in the void, living on borrowed time. Our bodies, our thoughts, our histories, all of it owed back to the abyss. It is difficult not to hear in this a whisper of mortality. Just as virtual particles vanish, so too will we. The difference is only scale, only duration. For the cosmos itself may one day balance its books, returning every flicker to the silence from which it came. But there is another way to look at it, that the uncertainty principle is not a loophole but a gift, a law that allows creation. Without uncertainty, the universe would be static, frozen, lifeless. With it, reality is restless, dynamic, alive. The ghosts of the void are the price we pay for a universe capable of birth and change. Perhaps the debt is not a flaw but a feature. Perhaps existence is not about permanence but about the dance of borrowing and returning, the rhythm of flicker and fade. Still, the question persists. If everything exists on borrowed energy, what secures the loan? Who or what ensures the debt can be paid? And what happens if it cannot? Physicists assure us the laws of conservation remain inviolate, that every loan is repaid, every fluctuation erased. But the unease lingers. For if reality tolerates impossibilities for a moment, what prevents it from tolerating them forever? If particles can cheat existence briefly, could universes do the same? Could we ourselves be the product of a cosmic theft, a fluctuation that refused to vanish? The thought is dizzying, terrifying, liberating, that everything, galaxies, stars, life itself, is one vast fluctuation, that we are not permanent but persistent, not inevitable but tolerated. And this brings us to the brink of another paradox. If borrowed energy sustains us, then perhaps the universe itself is nothing more than the longest-lived virtual particle, a fluctuation on the grandest scale waiting to dissolve. The uncertainty principle does not forbid it. Indeed, it may demand it. And so the ghosts of the quantum world remind us of a truth we would rather ignore, that existence is fragile, provisional, conditional, that the ground beneath us is not solid, but trembling with uncertainty. We live in a universe that borrows from nothing, a universe whose very fabric is credit extended by the void. And if that is so, then the next question is even darker. What happens if the void calls in its debt? At first glance, the universe appears solid. The chair beneath you, the floor under your feet, the stone of a mountain, the fire of the sun. We live in a world of tangible things, of matter that seems unyielding, substantial, undeniable. But peel back the skin of reality, descend into the realm of the quantum, and you find something unnerving. Solidity is an illusion. Every interaction, every force, every connection between particles is not direct but mediated by ghosts. The early 20th century saw physicists assembling the so-called particle zoo, a bewildering menagerie of leptons, quarks, mesons, baryons and bosons, each discovered in the violent collisions of accelerators or the traces left in cloud chambers. For a time it seemed the universe was built on a wild diversity of particles, like a bestiary of subatomic life. But as the dust settled, a deeper order emerged. Matter is built from quarks and leptons, the building blocks of atoms. Forces are carried by bosons, the exchange particles. And here the virtual enters again. For these force carriers, so vital to the architecture of the cosmos, are not always real. Most of the time, they exist only as virtual particles, unseen messengers darting between matter. Consider the electron, one of the simplest and most familiar of particles. When two electrons draw near, they repel each other like charges pushing apart. Classical intuition imagines this repulsion as a field stretching between them. But in quantum electrodynamics, it is explained differently. The electrons are exchanging virtual photons, ghostly quanta of light that are never observed, never captured, but whose passing conveys the force of repulsion. Without these phantom photons, atoms could not hold their electrons, chemistry would unravel, and life itself would never arise. The solidity of matter depends upon an invisible traffic of unreal messengers. Descend deeper into the nucleus of the atom, and the mystery grows darker still. Protons and neutrons cling together, bound by the strong nuclear force, a grip so powerful it overcomes the natural repulsion of their positive charges. But how is this possible? Inside, quarks are held tight by the exchange of gluons, particles that act like invisible threads, binding quarks into triplets, stitching protons and neutrons together. Yet most of these gluons, too, are virtual. They erupt in endless flurries inside the nucleus, exchanged at blinding speeds, never observed directly, yet indispensable. If they faltered for even a moment, every nucleus in the universe would disintegrate, stars would fall silent, the elements themselves would collapse, move outward again to the weak nuclear force, the strange interaction responsible for radioactive decay, for the fusion that fuels the sun. Its messengers are the W and Z bosons, massive particles that briefly flicker into the world in high-energy collisions. But within ordinary atoms, their role is again carried by virtual versions, fleeting exchanges that allow the nucleus to transform, to transmute one element into another. Here lies the paradox. Every atom in your body, every ounce of its stability, every flicker of its transformation depends upon particles that are not truly there. Forces are conversations between ghosts. Reality itself is a dialogue carried out by messengers who vanish before they can be caught. It is as if the entire universe is a séance, with unseen voices calling across the void, shaping matter with words we cannot hear. And what of gravity, the last great force? Here the mystery deepens into speculation. For decades, physicists have hunted the graviton, the hypothetical particle that would mediate the pull of gravity in a quantum world. If it exists, it may never be detected. And if it does not, then gravity may be the one force that resists the ghostly mediation of the virtual. But many suspect that even here, in the bending of space-time itself, virtual particles are at work in ways we do not yet understand. So the particle zoo, once imagined as a collection of tangible creatures, reveals itself as a hall of phantoms. The quarks and leptons are solid enough, enduring, measurable. But the forces that allow them to form atoms, molecules, stars, those are built on ghosts. Without the virtual, the real could not exist. Philosophers once dreamed of atoms as indivisible stones, the unshakable foundation of matter. Now we know that even atoms are woven from uncertainty, their forces carried by illusions. It is as though the cosmos has tricked us. Solidity is not built on rock, but on shadow. There is a poetic cruelty in this. The more deeply we search for reality, the less solid it becomes. We reach for bedrock and find mist. We chase particles and find probabilities. And when we ask how matter holds together, the answer is always the same, through exchanges of things that may not be real at all. This is where the unease creeps in. If every force depends upon virtual particles, then how real are the atoms themselves? Are they not too just temporary disturbances in deeper fields, defined by interactions with ghosts? The illusion multiplies. We begin to wonder if reality itself is nothing but a vast system of relationships with no true substance underneath. And yet, this illusion sustains everything. Your body, your thoughts, the earth, the stars, all of it depends upon these unseen messengers. Whether or not they are real, in the sense we demand, they are effective. They work. The universe could not exist without them. But the paradox remains unresolved. Are these particles genuine actors in the drama of physics, or are they lines in our equations, convenient fictions we mistake for players? Do we live in a haunted cosmos, or are we haunting ourselves with symbols? Either way, the conclusion is haunting. The solidity of the world, the tangibility of our lives, rests upon a scaffold of ghosts. And this leads to the next, more unsettling revelation. For if virtual particles can build matter, they may also build universes. In the restless storm of the vacuum, in the flicker of fluctuations, lies the possibility of creation itself. Entire galaxies, perhaps entire realities, born not from permanence but from flickers that refuse to die. Which begs the next question: what happens when nothing itself decides to create? Close your eyes and imagine the universe in its first breath, not the stars, not the galaxies, not even atoms, but a seething blur of energy, a newborn cosmos exploding outward from a state of unimaginable density. From that chaos, structure emerges, patterns form, matter condenses, and galaxies take shape. But the question that haunts us remains: what lit the spark? What transformed nothing into something? Quantum physics whispers an unsettling answer. Perhaps nothing itself did. The quantum vacuum is not barren. It seethes with fluctuations, with virtual particles appearing and vanishing in endless cycles. To most of us, these are ghosts too fleeting to matter, too fragile to leave behind anything lasting. But in the earliest moments of the universe, these fluctuations may have been magnified to cosmic scale. What was once ephemeral became permanent, frozen into the fabric of space-time itself. This is the foundation of inflation theory. In the fraction of a second after the Big Bang, the universe is thought to have undergone a period of runaway expansion, doubling in size again and again at breakneck speed. During this inflation, quantum fluctuations in the vacuum were stretched across cosmic distances, etched into the very structure of the universe. Tiny ripples in the quantum fields became the seeds of galaxies. The places where fluctuations were slightly denser became the sites where matter gathered, clumped, and eventually ignited as stars. The entire cosmic web, The grand scaffolding of galaxy clusters stretching across billions of light years may be nothing more than a magnified echo of the flickers of virtual particles in the infant universe. In other words, everything we see may have been born from ghosts. This is not speculation in the abstract. We can still see the fingerprints of those fluctuations today, frozen in the cosmic microwave background, the faint afterglow of the Big Bang. Look closely at that ancient light, and you find tiny variations in temperature imprinted more than 13 billion years ago. Those variations match the patterns predicted by quantum fluctuations stretched by inflation. The whispers of virtual particles magnified to the scale of the cosmos. It is a revelation that borders on the mythic. Ancient civilizations spoke of creation arising from chaos, of the cosmos born from void and darkness. And now physics tells a similar tale, that the most enduring structures in existence emerged from emptiness, that nothingness, restless and alive, created everything. But what does it mean to say that nothing created something? The very phrase feels absurd. How can the void give birth? How can absence yield presence? The answer lies in the slipperiness of the quantum vacuum. It is not nothing in the common sense. It is not absence. It is a sea of potential, a stage upon which possibility constantly flickers, even if most of those flickers fade. The early universe may have provided the perfect conditions for those flickers to persist, to crystallize into being. Here lies a paradox. Virtual particles are defined by their transience. They borrow energy, they repay it, they vanish. But inflation may have taken those temporary disturbances and amplified them so swiftly, so powerfully, that they could not vanish. They became real. They became us. If this is true, then the universe itself may be the child of a fluctuation, a vast and enduring reality born from the most ephemeral of beginnings. Our galaxies, our stars, our lives, the descendants of a ghost that refused to fade. It is a breathtaking, humbling thought. That existence is not the natural state, but the exception. That reality itself may be a ripple, a disturbance in a greater void. And yet the idea is not without its darkness. If fluctuations can create universes, they may also destroy them. Just as the vacuum seethes with temporary appearances, so too may it harbor the seeds of collapse. Some physicists warn of vacuum decay, a hypothetical event where the vacuum we know is not the true ground state of reality. If a deeper, lower energy vacuum exists, the universe could one day tunnel into it, rewriting the laws of physics in an instant. Galaxies, stars, life, all annihilated, erased by the collapse of the void itself. In this possibility, we glimpse the dual face of nothingness. It is both creator and destroyer, the womb of galaxies and the abyss that may unmake them. So, which is it? Is the void our mother or our executioner? Perhaps both. Perhaps creation and annihilation are two sides of the same coin, flipped endlessly by the hand of quantum uncertainty. For us, the implications are more intimate. If galaxies themselves are born from fluctuations, then so are we. Every atom in your body, every neuron in your brain, traces back to a ripple in the early universe, a flicker in the void stretched across light years. You are not simply in the universe, you are the echo of its first fluctuation. You are, in a very literal sense, a child of nothing. And so the ghosts of the quantum world remind us of an unsettling truth. Nothing is not empty, nothing is potential, nothing is the restless soil from which reality grows. But this truth comes with a question too profound to ignore. If something can be born from nothing, then is nothing ever truly nothing? Or is the void itself the ultimate something, a sea of possibility more fundamental than matter, energy, or even time? We end here with the unsettling image of a cosmos that is not built on permanence, but on flickers. That the most enduring structures in the universe, galaxies, stars, life, are the crystallized echoes of ghosts. And the next question presses close. demanding an answer. If we can see the fingerprints of these ghosts etched across the heavens, can we also catch them in the laboratory? Can we prove their existence not just in theory but in experiment? The answer awaits, hidden in the precision of our instruments, in the trembling of particles, in the shadows of collisions. Because sometimes the unreal leaves scars on reality itself. The ghosts of the quantum world are, by definition, unseen. They flicker into being and vanish before they can be caught, leaving only the faintest tremors in their wake. But physics is nothing if not relentless. If something influences the universe, however fleetingly, then there must be a way to detect its shadow. And so, across the last century, physicists have turned their instruments toward the impossible, searching not for the ghosts themselves, but for the scars they leave upon reality. The first evidence lay not in giant machines, but in mathematics. Quantum electrodynamics, QED, describes how charged particles like electrons interact with light. It is the most precise theory ever built, so accurate it has been compared to predicting the width of North America to the thickness of a human hair. But here's the haunting part. The precision comes only when virtual particles are included. Remove them, and the numbers fall apart. The very accuracy of our predictions is a fingerprint of the unreal. Consider the electron. At first glance, it seems simple, a fundamental particle, indivisible, a point charge. But in reality, it is dressed in a cloud of virtual particles. Around every electron, virtual photons flicker in and out, briefly existing, warping its charge. Sometimes even pairs of virtual particles erupt, electron and positron, adding their own distortions. The result is that the electron's magnetic moment, the way it responds to magnetic fields, is slightly altered. Physicists have measured this value with exquisite care, and the result matches theory to better than 1 part in a trillion. That level of accuracy is only possible if the ghosts are real in some sense. You cannot see them, but their presence shapes the world so precisely that without them, our predictions would be wrong. The invisible has left its mark. But theory alone was not enough. We demanded evidence in the flesh of experiments, in the roar of colliders, in the precision of detectors. In particle accelerators like CERN's Large Hadron Collider, beams of protons collide at near light speeds, smashing matter into showers of fragments. These collisions are more than destruction. They are revelations. When particles are torn apart, the fingerprints of virtual interactions are revealed. Rare decays, unexpected scattering patterns, anomalies in particle lifetimes, all of these hint at the influence of virtual particles mediating events. One of the clearest examples comes from something known as vacuum polarization. Imagine 2 electrons repelling each other. In classical physics, their force is clean, predictable. But in reality, the vacuum between them is restless. Virtual electron-positron pairs erupt, screening the charges, modifying the force. This changes how the electrons scatter when fired at one another. The effect has been observed. It matches the predictions of virtual particles. Once again, the invisible has left scars we can measure. Then there is the Lamb shift, a subtle alteration in the energy levels of hydrogen atoms. According to classical theory, the electron in a hydrogen atom should occupy precise energy states, like rungs on a ladder. But when physicists measured these levels with extraordinary precision, they found tiny deviations. The culprit, virtual photons, constantly flickering around the electron, nudging its energy, shifting its orbit. The Lamb shift is a whisper of ghosts, written into the spectrum of the simplest atom. Everywhere we look closely enough, the same story unfolds. Tiny discrepancies, minute shifts, delicate anomalies, each pointing toward the same conclusion. The vacuum is not empty. It is alive, and its restless fluctuations leave fingerprints on matter itself. Yet the most haunting experiments are those that blur the line between theory and reality entirely. In recent years, researchers have probed the quantum vacuum by creating conditions where virtual particles are coaxed into becoming real. This is called the dynamical Casimir effect. By rapidly moving mirrors at near-light speeds or by manipulating superconducting circuits, scientists can force the vacuum fluctuations to manifest as actual photons of light. Ghosts are made flesh. It is a reminder that the boundary between real and virtual may be thinner than we imagine. What we dismiss as unreal may only be waiting for the right conditions to reveal itself. And yet questions remain. Are these virtual particles real entities, fleeting but genuine? Or are they just mathematical tools that happen to match reality with uncanny precision? The experiments prove their influence, but not their existence in the way we define existence. They are shadows without a source, echoes without a voice. Perhaps the deeper lesson is this. Reality does not care for our categories. The universe is not obliged to tell us what is real or virtual. It only reveals patterns, consequences, behaviors. We are left to interpret them, to wrestle with what it means when the unreal leaves scars upon the real. There is a philosophical chill in this realization. For if the universe itself does not distinguish between real and unreal, then perhaps the boundary exists only in our minds. Perhaps what we call real is simply that which persists long enough for us to notice, while the virtual flickers too quickly to be seen. But both leave their mark. Both shape the cosmos. Think of a dream. While you dream, the experience feels real, vivid, undeniable. Only upon waking do you dismiss it as unreal. But in its time, it shaped your thoughts, your feelings, perhaps even your actions the next day. Virtual particles are the dreams of the vacuum. They may vanish quickly, but their influence is undeniable. So what do we call real, the things we can see and touch, or the things that shape the world, however fleetingly? Physics cannot answer this. It can only measure the shadows. And so, as our colliders roar, as our detectors hum, we continue the hunt. Not for the ghosts themselves, but for the scars they leave behind. The Lamb shift, the anomalous magnetic moment, vacuum polarization, the dynamical Casimir effect, each one a whisper from the void, telling us that the unreal is not only present but essential. Yet the deeper we listen, the stranger the story becomes. For the ghosts of the vacuum do not just nudge electrons or shift energies. They may hold the key to the greatest paradox in physics, the black hole information problem, the stability of the vacuum, the very fate of the universe itself. Because if the unreal can leave marks, then perhaps it can also rewrite the fabric of reality. And that leads us into the next revelation. When physics itself confronts philosophy, and we are forced to ask, what does it mean for something to exist? What does it mean to exist? It is a question as old as thought itself. Philosophers have argued for millennia over the nature of reality, whether it is made of substance or ideas, whether what we perceive is truth or illusion. And now, in the strange theater of quantum physics, the question has returned with new urgency. For the ghostly figures we call virtual particles sit uneasily between existence and non-existence, daring us to decide which side of the boundary they occupy. Physics is usually a science of precision. We define, we measure, we predict. Yet here language falters. We call them particles, but they cannot be caught. We call them virtual, but they leave scars on reality. Are they fictions, or are they truths wearing a disguise? The debate is not just semantic. It cuts to the heart of what we mean by real. The Copenhagen interpretation, one of the oldest lenses through which quantum mechanics is viewed, warns us to tread carefully. According to its philosophy, the mathematical formalism is not a literal description of what exists. It is a tool to predict outcomes of experiments, nothing more. In this view, virtual particles are simply steps in a calculation, like scaffolding used to build a house and then discarded. They are not real. They are the mathematics we use to reach reality. But others take a harder stance. The many worlds interpretation insists that quantum processes are not about probabilities, but about branching realities. Every possibility occurs, every path is taken, Each flicker of a particle splits the universe into new versions of itself. If this is true, then perhaps even the fleeting ghosts of the virtual world are real. Not here, not in this branch, but in another. Then there are those who follow de Broglie and Bohm with their pilot wave theory. Here, particles have definite paths, guided by hidden waves of information. Virtual particles in this view are not actual things, but ripples in a deeper, unseen field. They are not fictions, but shadows of an order more fundamental than our mathematics reveals. The question resists resolution because it is not just physics. It is ontology, the study of being. Can something be considered real if it is unobservable, if it vanishes before it can be measured? Or does reality require endurance, presence, interaction? Some philosophers argue for instrumentalism. If it works, if it predicts, if it shapes experiments, then it is real enough. Others demand stricter standards. Reality must be independent of the observer, independent of the equations. Virtual particles, by this measure, fall short. But physics complicates the issue, for the universe itself behaves as though they exist. The Lamb shift, the Casimir effect, Hawking radiation, these phenomena are as real as gravity, as light, as matter. To deny virtual particles is to deny the evidence of their influence, and yet to affirm them as real requires redefining what reality means. Perhaps then the problem lies not with the particles, but with us. Perhaps our categories, real, unreal, true, false, are too crude for a quantum world. The universe may not fit neatly into the boxes of our language. It may not care about our definitions. This is a humbling possibility, that our deepest philosophical instincts are outdated tools, useful in daily life, but inadequate for the abyss. We crave permanence, substance, solidity. But the quantum world offers only flickers, fluctuations, relationships. Perhaps reality itself is not made of things but of interactions, not of objects but of processes. If so, then virtual particles may be as real as anything else. They are not objects but events, not stones but whispers, not permanent but effective. This echoes ancient philosophies. The Buddhist notion of impermanence, the Greek idea of flux, the mystical concept of creation from nothing, all suggest that reality is less about enduring substance than about constant becoming. Virtual particles fit neatly into such visions. They are not illusions, but evidence that the universe is made not of things but of changes. And yet, the unease lingers. For if reality is built upon fluctuations, what becomes of truth? What becomes of permanence? What becomes of us? Are we nothing more than long-lived virtual particles, flickers in a cosmic field destined to vanish? Here, philosophy offers no comfort, but perhaps it offers perspective. To say we are flickers is not to say we are meaningless. A lightning bolt vanishes in an instant, yet it lights the sky. A melody fades as soon as it is played, yet it lingers in memory. Existence need not be permanent to be profound. The philosophers at the horizon stand with us, gazing into the quantum abyss. They remind us that science does not abolish philosophy, but revives it. That physics does not escape questions of being, but sharpens them. Virtual particles force us to confront what we mean by real, and perhaps to admit that our categories must evolve. For the next horizon awaits, darker still. If the vacuum is not empty, if it teems with fluctuations, then perhaps emptiness itself is an illusion. Perhaps nothing does not exist at all. And that brings us to the next revelation, a thought that chills the spine. If even the void is alive, then where in this universe can true nothing be found? For most of human history, emptiness was imagined as the simplest of all things, a void. A blank canvas, a space where nothing happens and nothing exists. Philosophers argued about whether such a void could truly exist, but in the popular imagination, the answer seemed obvious. Empty space was absence, the backdrop to reality, not reality itself. But quantum physics has destroyed that illusion. Emptiness, it turns out, does not exist. Take any region of space, strip it of all matter, remove every atom, every molecule, every grain of dust. Let the temperature fall to absolute zero, colder than the deepest intergalactic void. What remains? Intuition says, nothing. But the truth is stranger. Even in the most perfect vacuum, something remains. Space itself is alive with restless activity. This is the quantum vacuum, the ground state of the universe. To the eye it appears featureless, to instruments it seems empty, but beneath the surface it seethes. Virtual particles erupt into being, borrowing energy from uncertainty, then vanishing again. Electromagnetic fields ripple with fluctuations, invisible currents dance in silence. Emptiness is a mask. Behind it lies an ocean. The illusion of emptiness was broken not by philosophy but by experiment. The Casimir effect showed us that two metal plates in a vacuum are not suspended in stillness, but pushed together by the pressure of fluctuations between them. The Lamb shift revealed that hydrogen atoms carry scars from ghostly photons flickering around their electrons. Even the structure of galaxies may bear the fingerprints of quantum fluctuations magnified by cosmic inflation. All of these are proofs that emptiness is an illusion. The void is not void at all. This realization reshapes our sense of reality. If space itself is alive, then the universe is not built on a foundation of nothing, but on ceaseless motion. The stage is as active as the play. The backdrop is part of the drama. Consider the implications. Every cubic centimeter of empty space contains more activity than the surface of a star. The vacuum is filled with potential energies, with fleeting particles and antiparticles flashing into being. Their average effect may cancel out, leaving the void apparently calm. But beneath the averages, the dance never ceases. Nothingness is noise. This has consequences not just for physics, but for philosophy. The idea of emptiness as absence, as a state of pure nothing, collapses. The void is no longer the opposite of being. It is a form of being. A restless presence masquerading as silence. Perhaps this is why the word vacuum feels inadequate. It suggests a barren space drained of content. But the quantum vacuum is crowded, seething. To call it empty is to mistake the surface for the depths. And yet, there is a darker undertone to this realization. If the vacuum is alive, if fluctuations cannot be suppressed, then stability itself is an illusion. Reality rests upon restless foundations. The quiet of the night sky, the stillness of intergalactic space, is not calm but chaos wearing a mask. This raises a chilling possibility. If emptiness is never truly empty, then perhaps the universe can never truly rest. The fluctuations may not merely shape matter, but may dictate the destiny of the cosmos. Some physicists whisper of vacuum decay, the possibility that what we call empty space is not the true ground state of reality, but a metastable illusion. If so, the vacuum could one day collapse into a deeper state, rewriting the laws of physics in an instant, erasing galaxies, stars, life. The illusion of emptiness may hide not only activity, but danger. But there is another way to see it. The restlessness of the vacuum is also the source of creation. Without fluctuations, galaxies would never have formed. Without vacuum energy, the cosmos would not expand. Without the illusion of emptiness, there would be no existence at all. So which is the truer face of the void, creator or destroyer? Perhaps both. Perhaps the void is not emptiness at all, but duality. Silence and storm, absence and presence, death and birth. Imagine the night sky again. You look into the darkness and believe you're staring into emptiness. But in truth, every inch of that darkness is alive, filled with flickers too fast for your eyes to see, too small for your instruments to detect. A restless cosmos hiding in plain sight. This is why the illusion of emptiness is so powerful. It deceives us into thinking that silence is nothing, when in truth silence is simply a sound we cannot hear. And so we are forced to abandon one of our oldest intuitions. Nothing does not exist. Emptiness is not real. The void is not absence, but presence of another kind, a presence so pervasive, so subtle, that we mistake it for nothing at all. This realization transforms the way we see ourselves. For if even the void is alive, then life itself is not an anomaly but a continuation. We too are fluctuations, longer lived, more complex, but born from the same restless ocean. Our existence is not built on emptiness, but on the ceaseless activity of the void. But there is one more layer to this illusion, and it is darker still. If emptiness is an illusion, then perhaps solidity is as well. If even the void is restless, then what of matter itself? What if everything we call real is merely the surface of a deeper turbulence? The illusion of emptiness, once pierced, leads inevitably to another question. If the void is alive, then what lies beyond it? What deeper reality does it conceal? And this brings us to the horizon of dread. The possibility that our universe itself is not final, not fundamental, but a temporary fluctuation. That we are living in a false vacuum, balanced precariously above a deeper abyss. If emptiness is an illusion, then perhaps existence is too. Picture the universe as a vast stage, its curtains made of stars, its floorboards woven from space-time itself. For billions of years, the play has unfolded, galaxies forming, stars igniting, life flickering into being on fragile worlds. To us, it feels eternal, unshakable, as though the cosmos itself is the bedrock of reality. But what if the stage itself is unstable? What if the universe is not built on permanence, but on a fragile illusion waiting to collapse? This is the specter of vacuum decay, one of the most unsettling possibilities in physics. The quantum vacuum, restless and alive, may not be the true ground state of reality. It may be what physicists call a false vacuum, a metastable condition that appears stable for now, but hides a deeper, lower energy state beneath. If this is true, then everything we know, matter, energy, the laws of physics themselves, rests upon a fragile plateau. And one day, it may fall. The mechanism is terrifying in its simplicity. Quantum fields define the structure of reality, and one of the most important is the Higgs field, the invisible energy that gives particles their mass. Measurements of the Higgs boson suggest that the universe may not be perfectly stable. Instead, we may live in a precarious balance, like a ball resting in a shallow hollow with a deeper valley lurking nearby. A small disturbance could push the ball over the edge. If that happened, the vacuum would decay. A bubble of true vacuum would form somewhere in the universe, expanding outward at nearly the speed of light. Inside the bubble, the laws of physics would be rewritten. Particles as we know them would not exist. Atoms would dissolve. Chemistry would vanish. Stars and galaxies would be unmade. Life would be impossible. And because the bubble would expand at light speed, there would be no warning, no escape. One moment, the universe. The next, nothing. It is perhaps the most chilling vision science has ever produced. Annihilation not by fire or collapse, but by silence. Not by something, but by nothing. For now, the threat is hypothetical. The timescales are vast, perhaps trillions of years. Or perhaps the decay will never happen at all. But the mathematics does not let us look away. The possibility lingers like a shadow at the edge of reality, reminding us that existence may be more fragile than we dare to believe. What makes this prospect so haunting is not just the destruction it implies, but what it reveals about our definition of reality. If the universe can be rewritten in an instant, if the laws of physics themselves can change, then what does it mean to call anything fundamental? What is permanence when the very fabric of existence is provisional? Perhaps the scariest truth is that there would be no sign of approaching doom. No cosmic warning, no subtle tremors. The bubble would arrive unannounced, rewriting reality before a single neuron in your brain could fire. The end of the universe would come faster than thought. And yet, Even in this abyss, there is wonder. The fact that we can imagine such an end is itself extraordinary. That human beings, fragile creatures of carbon and water, can stare into the void and grasp that the universe may be precarious, that our reality may be a fluctuation balanced on the edge of collapse. There is also a strange kind of mercy in the vision. If the bubble of true vacuum were to arrive, we would not suffer. We would not even know. The transition would be instantaneous, silent, absolute. Not apocalypse, but erasure. Not fire, but forgetting. But this is cold comfort, for the idea itself is enough to unsettle. It reminds us that the universe is not built for our reassurance, that existence is not guaranteed, but borrowed, that permanence is an illusion. This is why vacuum decay is not just physics, but philosophy. It forces us to confront the fragility of reality, the possibility that what we call existence is conditional. It suggests that even the laws of nature are not eternal, but local, temporary, provisional. That there may be a deeper reality beneath, waiting to overwrite ours. And it raises a haunting question. If our vacuum is false, what lies within the true? What would reality look like in its deeper state? Would it be a place of silence and nothingness, or a realm of new laws, new structures, unimaginable forms of being? Would it be emptiness, or would it be another universe altogether? The possibility chills and excites in equal measure. It reminds us that the edge of knowledge is not a wall, but a cliff, and beyond it lies an abyss we cannot yet see. This is the edge of reality, the place where physics admits its limits, where our equations point to horrors we cannot test, where our knowledge collides with the unknowable. And standing here, we are forced to admit how fragile our place is. Perhaps the greatest irony is this: the same virtual particles that give us stability may one day be the seeds of our destruction. The fluctuations that hold atoms together, that fuel the sun, that seeded galaxies in the young universe, those same ghosts may trigger the collapse of the vacuum itself. Creation and destruction are bound together, the womb and the tomb are one, so we live on the edge, balanced on the tremors of nothingness. The illusion of stability comforts us, but the truth waits in the shadows. That the universe may not be eternal, that reality itself may be contingent, that existence is a flicker, waiting to vanish. And this leads to the next haunting reflection. If the universe itself is a fluctuation, balanced on borrowed stability, then what of us? Are we not mirrors of that same fragility? Are we not too flickers on the edge of reality, borrowing our time before vanishing into silence? The ghosts of the vacuum draw us to the edge, whispering the same question that has haunted philosophers and physicists alike. Is permanence an illusion? And if it is, then what does it mean to live in a world that trembles on the brink of disappearance? What we discover in the quantum abyss is never just about physics, it is about ourselves. The strange truths of virtual particles, of vacuums alive with ghostly fluctuations, echo far beyond equations. They force us to confront what it means to exist, not just for the universe, but for us. For if reality itself is fleeting, provisional, unstable, then so too are we. Look at a human life. From the grand vantage of the cosmos, it is little more than a flicker, a brief flame against the dark. A century at most, measured against billions of years. Even entire civilizations rise and fall in the blink of cosmic time. What is Rome? What is Babylon? What is all of human history compared to the lifespan of a star? And yet within that flicker lies meaning, memory, consequence. We live as though permanence is our right. We build monuments in stone, we write histories, we pass down names. We imagine that through these we defy the silence, but the silence always comes. Entropy erodes, memories fade, even stars will burn to embers. What we call permanence is, like the quantum vacuum, only a fragile illusion. And here is the unsettling resonance. Our lives are like virtual particles. We appear, briefly, shaped by uncertainty, borrowing energy from the void of time, and then we vanish. We exist long enough to interact, to influence, to leave fingerprints on the fabric of others' lives. But we cannot remain. We are temporary by design. This should terrify us, and yet, perhaps it is the very source of meaning. The ghosts of the quantum world remind us that reality is not about permanence, but about effect. A virtual photon may exist only for an instant, but in that instant it shapes the universe, binding electrons, building atoms, holding together the matter of stars. Its value lies not in how long it endures, but in what it makes possible. So too with us. We may vanish, but while we are here, we can alter the course of lives. We can ignite love. We can kindle knowledge. We can carry memory forward. Our reality is not measured in endurance, but in influence, not in permanence, but in presence. In this sense, human life mirrors the cosmos itself. The universe too may be temporary, a fluctuation, a borrowed state. But within that fluctuation, galaxies have bloomed, stars have burned, and life has looked back at the void in wonder. Perhaps permanence is not required for meaning. Perhaps meaning is born in the flicker. There is a strange beauty in this. To know that we are temporary is to know that every moment matters. Every breath, every word, every kindness or cruelty is a ripple in the fabric of a fragile world. We are the ghosts of the void, granted a longer lease, given the chance to shape reality before we fade. And if the universe itself is a fluctuation, then perhaps we are its consciousness. Perhaps our thoughts, our questions, our awe are the way the void reflects on itself. The universe has borrowed time, and in that time it has created us, beings who can marvel at the lone. This reflection forces us to ask, is permanence truly what we seek, or is it depth? Is it endurance, or is it intensity? A lightning bolt lasts but a second, yet it can split a tree, ignite a fire, illuminate the sky. So too with us. Perhaps the lesson of the quantum ghosts is not despair, but responsibility. If we are flickers, then what do we choose to illuminate? If we are whispers, then what words do we leave behind? The parallels grow deeper. Just as virtual particles cannot be seen directly but only inferred from their effects, so too are we. Long after we vanish, it is not our bodies that remain but our traces, the love we gave, the ideas we sparked, the lives we touched. We are judged not by endurance but by influence. And there is one more haunting connection. The uncertainty principle, which allows virtual particles to exist, also governs us. We cannot know all things with certainty. We live within limits of perception, of time, of understanding. We are, like the quantum world, defined as much by what cannot be known as by what can. This should humble us. It should remind us that to live is to live in uncertainty, to embrace the flicker without demanding permanence. But here lies the wonder. In the very act of questioning, we transcend. In gazing into the void, we carve meaning out of silence. We become more than flickers. We become the flame. Perhaps that is why the universe tolerates us, why this fluctuation has persisted long enough to create galaxies, stars, and thinking beings. Not because permanence is the goal, but because meaning is possible even without it. We live as echoes of ghosts, but we are echoes that sing. And so, when we confront the fragility of existence, when we feel the dread of impermanence, perhaps the right response is not fear, but awe. To stand in wonder at the fact that anything exists at all. That in the restless sea of the void, this fluctuation, this universe, this life, this moment was allowed to be. In this way, we are the human mirror of the virtual world. Our reality is borrowed, our time uncertain, our permanence an illusion. But our influence is real, our presence undeniable, our meaning profound. And this brings us to the closing of our journey. For if the universe itself is a fluctuation, if we are flickers within flickers, Then the final question presses against us like the silence of the void. What remains when the fluctuation ends? The journey ends as it began, in the shadows of the void, where the line between existence and nothingness blurs. We set out asking if virtual particles are even real, and we arrive at an answer that is not an answer at all. For reality itself may not be real in the way we once believed. It may be flicker, fluctuation, ghost. Think of the universe now, a vast expanse of galaxies, stars, planets, and people. It feels so solid, so undeniable, so permanent. And yet beneath it all lies the seething quantum vacuum, restless, uncertain, alive. Ghosts flicker through every atom, every force, every heartbeat. They bind the nucleus, they push galaxies apart, they devour black holes. Without them, there is no cosmos. Without them, there is no us. But they are not real, not in the way we crave. They cannot be caught, they cannot be owned. They exist only in their effects, their scars, their whispers. They are shadows cast by mathematics, and yet they shape the fate of stars. Perhaps then reality itself is a ghost, not substance but process, not permanence but interaction, not things but relationships. If this unsettles you, it should, for it means that the universe is not built on bedrock, but on storm clouds, that our foundations are trembling seas, that permanence is the grandest illusion of all. And yet it is also liberating, because if reality is flicker, then meaning is not found in endurance, but in presence, not in eternity, but in the moment. Just as virtual particles live briefly yet shape the world, so too do we. Our lives may be finite, our time borrowed, but what we do in that time reverberates. A kindness, a thought, a discovery, all are ripples in the great fluctuation. In this way, we are ghosts in the machine, just as much as the particles we study. The universe is the machine, vast and intricate. We are the ghosts flickering through it, shaping it, and in turn being shaped by it. This is the final symmetry. The micro and the macro, the human and the cosmic, mirror one another. Virtual particles borrow time from the void, so do we. Virtual particles influence without being seen, so do we. Virtual particles vanish, leaving only scars on the fabric of reality, so too will we. And yet the story is not despair, it is wonder. For the fact that we exist at all, that the void tolerates us, that the fluctuation persists long enough for thought, for love, for awe, is a miracle beyond comprehension. Nothing could have been, and yet something is. Perhaps that is the ultimate lesson of the ghosts. That reality need not be permanent to be profound. That existence, fleeting though it may be, is still enough to light the darkness. So when you look into the night sky, when you see the stars scattered across the void, remember, you're looking not into emptiness but into a restless ocean. Every photon, every atom, every galaxy is born of fluctuations, borrowed from the vacuum, written in the language of uncertainty. You are not outside of this, you are part of it. You are the universe, contemplating itself. And when your time comes to flicker and fade, as it will, know this. You will not vanish without consequence. Like the ghosts of the quantum world, you will leave your mark. A ripple in the lives you touched, a scar in the fabric of memory, an echo in the great machine. Are virtual particles even real? Perhaps the answer is the same as for us. Real enough to matter, real enough to change the universe, real enough to leave echoes that never truly die. And so we close our journey not with certainty, but with awe. For we have glimpsed the ghosts that underlie existence, and in them we have glimpsed ourselves. The cosmos is haunted, and we are its haunting. In the end, what have we truly uncovered? Not an answer in the form we first sought, not a tidy declaration of yes or no, not a neatly defined category where we can place these strange phantoms of the quantum world. Instead, what we have uncovered is a mirror that reflects back to us the limits of our knowledge, the fragility of our definitions, and the profound strangeness of the cosmos. We began with the smallest of questions. Are virtual particles even real? Yet, as so often in physics, the smallest question led to the largest horizon. In chasing ghosts at the edge of existence, we have discovered that the boundary between real and unreal is not sharp, but blurred. That the universe itself may not be built from objects at all, but from interactions, fluctuations, processes. That permanence, the thing we crave most, the thing we imagine in the stars and in our monuments, may not exist anywhere in nature. This does not make the world less meaningful. On the contrary, it makes it more extraordinary. For if everything is fluctuation, then the fact that such fragile flickers can assemble into galaxies, into stars, into life, into us, is nothing short of miraculous. We are the children of instability, the offspring of uncertainty, the inheritors of a cosmos built on borrowed time. And yet, within that fragility, beauty emerges. The ghosts of the quantum world remind us that meaning is not found in endurance but in presence, not in how long something lasts, but in what it makes possible while it is here. A virtual particle may live for a trillionth of a second, and yet without it, atoms would fall apart, stars would not burn, galaxies would never form. So too with us. Our lives are brief, but they carry weight. They bind, they ignite, they give structure to the universe of human memory. And so perhaps the true lesson of this journey is that reality is not a matter of substance, but of influence. That what is real is not what lasts, but what shapes. That even ghosts can alter the destiny of the cosmos. This realization should not terrify us, it should awaken us. For if the universe is a restless sea of flickers, then every moment is precious. Every thought, every word, every kindness is itself a fluctuation, a ripple in the great ocean of being. Nothing is wasted, nothing is without consequence. And in this way, we come full circle. The question was about particles, but the answer is about us. We are not outside of this strange, flickering universe. We are expressions of it. We are the fluctuations made conscious, the ghosts given voice. The cosmos is restless, and so are we. The void is alive, and so are we. So the next time you stare into the night sky, do not see emptiness. See possibility. See the restless ocean beneath the silence. See the ghosts that bind the stars. And know, in that moment, that you are one of them. Fleeting, fragile, and yet essential. A flicker in the void, yes, but a flicker that matters. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.